So this is the module 4. We are in lecture 19, recent deep neural networks, a very quick and rough survey of selected trends. And we are finishing, I believe this is the last module of section 3. Okay, so we use the 7 variables to chunk the deep learning landscape. And we, in the module 1, we talked about using the data variable to chunk to the new trends, and then in the module 2 we talk about using the task variable to chunk the landscape. So in the module 3 we talked about using the representation and also the scoring and the search to chunk the literature. So now, like this is the last module, I will talk more about model properties and the metrics to evaluate what makes a good model, and also the adaptations of classic models into maybe more specialized hardware, like edge IoT type of hardware architectures. Okay, so first let's talk about model properties or metrics to evaluate the models. So there are a lot, because so as deep neural networks becomes so popularly applied to many different tasks. I mean, just really touches every part, many parts of our daily life or scientific fields, and then it becomes more and more like this, like a software management. So we, in the software engineering, we know we care about robustness, trustworthiness, and transparency and bias of our software, right? So everything of those are also applicable, should be taken care for those models you learned from data. So people actually call this software like a 2.0. So those models you learned from these kind of deep learning, machine learning formulations, they are also softwares. So you should try to have good management of the software of the models, and also guarantee and also measure and their properties. So the first very popular like kind of property of DNN, or people trying to spend a lot of time on, is to understand deep neural networks. So essentially our old metrics are more like performance, like you have a Y, there's a Y truth, there's also Y predicted. You're trying to evaluate maybe how close, how similar they are. So all those metrics we cover, like accuracy, F1, so on and so forth. Those are good, but they're not enough, because the models start to interact with the human users and user a lot. And there should be a level of interpretation that human can understand how those deep neural network models make decisions. So people kind of criticize DNN has this black box nature, and propose a lot of ideas trying to open the black box. So here is more like an overview of interpretation. So we can categorize this kind of understanding landscape into 2 kinds. So the first kind is more like a post hoc explanation. So we already have a DNN model. We try to explain. We try to post-processing to explain it. So there are classic method like feature visualization, feature attribution. You can do instance level attribution or model level attribution. You can also combine the two. There's also method called trying to attribute at the example level. So this is the first kind, post hoc explanation. There's another big group called inherently interpretable models. So it's a little vague, but some people think like linear model or tree models are more interpretable than deep neural network models. So here I show an image from this very great work from Deep Dream and doing feature visualization. So they are trying to visualize each neuron, what type of image. So that's the second row here. So for a specific neuron, and there's this neuron seems to the best activation image that activate that neuron seems to be a dog face. And you can actually get this best image, or maybe really great the optimization based good image that activate a specific neuron, and then they seems to be because this can be shown as an image, right? So you can visually eyeball to understand how different neurons differ from each other. Yeah, all right. So there are a lot, to play with the Deep Dream. I just highly recommend you to play with their website. All right, so that's the understanding deep neural networks, right? So there's another landscape of family of a method is trying to design images called adversary examples to fold the deep neural network models. So this is the most classic example. So initially this is a panda image, and then you try to add a very small noise. In this case, it's a super small noise. It's 0.07 times that noisy image. And then this generated image for the human eyes, this still look like a panda, right? Yeah, of course, this looks like a panda. But the deep neural networks, because this gradient-based noise, it's just so nicely crafted. And this will push the deep neural networks to predict this as a given, which is very interesting if you think about it, right? So from our visual perception, and these two images, this original image and this adversary image, they really look like alike, right? But why the DNN predict them wrongly? This create a lot of heated discussion and research about robustness of deep neural network models. And then very similar images like this school bus plus some kind of noise distortions, and then it still look like a school bus, but it will predict wrongly by a CNN models. And there's many examples you can find in the same group. So because robustness of the deep neural networks becomes a concern and raised by the adversary examples, and then there's a group, really a family of work verification called verifying deep neural networks, trying to check something called a local adversary robustness test. So how can we know? This a deep neural networks is provably robust. So there's a really big family of work in this direction. All right, so we talk about different kind of metrics of, So yeah, there's also some work about fairness of the neural networks and the biases. I did not get time to put in a slide about it, but feel free to use the keywords to search. And those are really important topics in evaluating deep neural networks in the current research. All right, so we talk about new metrics to evaluate the deep neural network models. And now let's shift to this hardware adaptations. So, so what do I mean hardware adaptation, right? So this is really with this background of edge devices. So the majority of the methods, so this is not about designing hardware for deep neural network models. Of course, there are people who do that, like a TPU, GPU, right? But what I focus here, it's more about how do you adapt those classic, very important deep neural network models like ConvNets, maybe transformer. Currently, how do you compress them to push them into edge devices? So why? Because this is a survey, a review organization. They were saying just the global IoT, there are just like billions of connected devices now, and everything becomes digital. So in the old days, right, the physical is more dominating compared to digital, right? But now we are really moving to the time that digital is more dominating with everything kind of virtual, right? So there are so many edge devices and also digital devices. They're not like the state-of-the-art GPU servers with enough GPU RAM, enough computation, but people use them a lot. Like people want to use their phones to do object detection, and people use Alexa to do speech recognition, use language translation, like autonomous decision makings, and we cannot just rely on the traditional type of programming to push into edge devices, right? So deep neural networks are such a powerful group family of models, but they are very costly. They are large in terms of RAM and also computational cost. How can we like adapt those powerful deep models into the edge devices as maybe less battery, like needs to be energy efficient, has less memory, has less computational threads. So how to do that? So there's a huge family of methods trying to solve this challenge. So we can roughly group them into three kinds. So there are model pruning based, there are this construction simplification based, there's also this quantization based. So inside the model pruning group, so there are magnitude-based pruning. There's also the Hessian-based pruning. You're really trying to prune those not very important neurons, not important filters, not important kernels, not important layers. That's the first kind, pruning. And the second kind is, so you try to decompose, so a lot of layers are super large, cause a lot of memory cost, right? Can you find a smaller, simplified version that almost as good as those very large blocks? So there are like many are decomposition based, like using matrix factorization, SVD based. There's also this flattened convolution based. So there's quite some work trying to simplify the current blocks into simpler filter. So that's the second kind. The third kind is, okay, so I have my my current models. So each of the weights using a float or maybe a double. Rather than using float, a double, can I make them into maybe a binary, which costs much smaller memory cost, right? So this is like in general called quantization based. So there are a classic work, I think it's called binary neural network. Oh, I see. Yeah, I don't have a slides about it, but just use the keywords called binary neural networks. There are a lot of really interesting work there. So here I showed you a pruning base. So essentially you just try to prune using this iterative retraining. So before pruning, you have all those connected connections, and after pruning, you got much sparse and sparse connections. You can prune out the connection, prune out the neurons. So it's a very simple but very effective strategy. All right, so now let's summarize. We are using this nutshell views trying to cover some of the selected trends. So in the data variable data coordinate, we covered DNN graphs and DNN on program induction. So in the task variable, we covered the three interesting tasks beyond the supervised prediction, which are generation tasks, reinforcement learning tasks, and learning to learn tasks. So in the representation, which we already covered into other lectures, and we actually talk about quantization in the hardware. So the representation variable and the hardware variable kind of combine together. And also in the representation, that using that variable, the chunk, we have to like kind of remind ourselves. So even though data and F seems to be disentangled, but the DNN literature, in fact, I mean, this data variable, the input data type, and this the topology F are very entangled. So, for example, two-dimensional regular grid type, mostly just CNN ConvNet architecture. This one-dimensional language type of style are now dominated by transformer or by the self-attention based topology. And the graph type are kind of dominated by graph neural networks topology. All right, so, and then we spent the whole module 3 talk about combine this using the search, using the loss function and the optimization variable together. So we actually focus on 3 workflows. So the first is the self-supervision based pre-training and fine-tuning workflow for learning good representation. And then the second workflow is the Generative Adversarial Networks. It's a really innovative workflow for generative modeling. And then the third workflow is this learning to search, learning to hyperparam to tune, this AutoML workflow. And then lastly is in this module we talk about adapt the current model to hardwares and also measure the models by considering beyond the prediction performance alone. All right, so this is the references, and this kind of finalize the lectures 19 and also finalize the section 3.
Great. So we finished the current module, and this specific ending clip is recorded after I finish all the 4 modules, and I realized my nutshell index page doesn't have the module segmentations. So here it is. So this page is better displaying how the module are related to the different elements of the nutshells, and also inside each module, and how are the topics, trend topics we selected. Okay, so great. I hope you enjoy the content and see you in the next module.